with one observation that we did in the last lecture, which has to do with the relative amounts of the different species of matter and energy in the universe. And we did this plot here of log of each one of these components against the log of the scale factor. And let's say that we are here today at EA is equal to 1, redshift of 0 here, so that will be 0 basically there. And for instance, we found that if you have some amount of dark energy or cosmological constant here, this is a nearly constant component. Now, we also know that we can reconstruct the matter density here, which has a dependence as a to the minus 3. And also we know that today we have about 0.02% in radiation, and this has a different time dependence. It goes like a to the minus 4. And again, I did something curved, which shouldn't be. It's really a straight line. So this goes to a to the minus 4, right? Yeah, this is terrible. Anyway, it's a straight line here, okay? Like this. All right. You get the idea, right? So that's radiation here. Let me put it in a different color here, right? And this means that if we look back in the history of the universe, even though right now here we have, as I told you, about 70% in dark energy, 30% in matter. That's what we call dust here, which has 0 pressure. And then really something like 2 times 10 to the minus 4 or 5, I don't recall, 4 or 5, let's say 4 of radiation. By the way, these amounts here, it's kind of harder to detect because you're making a measurement that's always in some sense related to the Friedmann equation. The first Friedmann equation, which is 3h squared plus 3k over a squared is equal to 8 pi g times rho. And these two are somewhat related to this relation there. However, in this case here, it's not like this because we can actually directly detect the photons which are just roaming about the universe. This is the so-called cosmic microwave background, of which I'll tell you in a second. So this, we know exactly what this is. We know the amount here. We know the absolute value. The other ones, they are kind of relative to the total amount in terms of the expansion rate through this equation here. In any case, what we can do here is that we can look back in time and we can say, okay, so if we look enough back in time here, this is the instant when matter and radiation were equivalent. So we call this A of equality or Z of equality. And the Z of equality is about 5,000. So that's when the universe had equal amounts of radiation and matter. And so in the very early universe, the universe was dominated by radiation, and this has some important consequences. And then after that, it becomes dominated by matter. So we can look back in time. For instance, if you look back, by the way, I can even draw this here. And in the way that I drew here, it's kind of I use an unfortunate too flat of the curve here, but basically if you use, let me just use a different color here. Well, I'll just use white. If you had curvature here, we know that the curvature today is almost negligible. It's something over here, but let's say that it was over here. Then it goes like h to the minus 2 here, right, in terms of an energy density. So in the past, it was even more irrelevant, right? So we can safely neglect curvature as you look back in time. Okay, so we can now imagine what the universe must have looked like and what are the processes that should have occurred in the past. So if you look back, in the past, okay, the universe is denser, it's hotter, there's more available energy around to do stuff. So for instance, if you can imagine that if you look back, so let me make a drawing here. Okay, so this is Earth here. We are here looking up at the universe with our telescopes or whatever, right? We have here our little house here. So we have basically Earth is over here. We are observing the universe from here, right? If we look back in the universe, right? Let's say that we have the redshift going like this. The scale factor is growing like this. Time is also going like this, right? What's happening also is that you can put some physical scales in here, and you can imagine that what's happening here is that as you go up here, the energy also is going up, the densities are going up, and more importantly, you can think of the temperature of the universe also going up. In fact, we know that the temperature is basically going like 1 over the scale factor. So it increases with time. You can imagine that this is happening. You cram things together more and more. They warm up. They heat up. Right? So you can imagine that if you go enough in the past here, let me just make one instant of time here. After this instant of time here, the universe was so hot that even atoms couldn't be neutral because there was enough roaming energy from the radiation to ionize those atoms. So basically, from this moment on, we had neutral atoms. And above this energy, we just have nuclei, protons, hydrogen, helium, and typically very small amounts of everything else because all the other heavier elements were created by stars much later. So heavier elements were created down here with stars. The universe only started with hydrogen, and after nucleosynthesis, helium also. Here is ionized matter. That means it's basically a plasma, a hot plasma here. Okay? So that's one thing. Well, you can imagine that you go even further back in time to an energy which is so high that even the atomic nuclei are not stable because you have enough energy to break the nuclei apart, right? That means a huge amount of energy, but still, if you go enough back in time, you must reach that point. So from here on, we have only protons, neutrons, electrons, photons, neutrinos, etc. From here on, you have the ionized nuclei of hydrogen, helium, plus electrons, neutrinos, and photons also. Okay, so these are some important phases of the history of the universe. I won't be talking too much about the moment when you allow protons and neutrons to join to form, for instance, deuterium, tritium, helium, and so on. This is called the Big Bang nucleosynthesis, but I don't have too much time to talk about this today. I'll just take it as granted, right? So what is, if you talk about energy, what is the energy scale that we are talking about here that separates the phase when the universe has only protons and neutrons versus the phase when the universe has actually some nuclei. Do you know the energy scale of the nuclear binding energies by memory, by heart? Anybody knows what is the scale? What are the energy scales here? No, electron volts are for the binding energy of electrons to atoms, right? What is the binding energy of the atomic nuclei, typically? Mega electron volts. So that energy is about MeV, right? Turns out that in actuality, that energy, where this happens, is a little bit lower because of an interesting fact, which I also won't have too much time to discuss, that basically in the universe, for each proton that you have about 1 billion photons, okay? So there's 1 billion photons for each proton. So there's so many photons around that even if you have a black body distribution that is relatively low energy or low temperature, you still have enough photons on the tail of that distribution to ionize your system, to break up your system. So it turns out that the energy here is a little bit below MeV. It's more like 0.2 MeV, okay? That's just because of the amount of photons, just sheer amount of photons that you have out there. Now, for the second question here, what is the typical energy? Now, for this phase, you already answered. This is typically electron volts. So for the hydrogen atom, it's 13.6 electron volts, but for the other atomic states, it's a little bit below, but that's typically also a few electron volts. It turns out that because of the same reason, there are 1 billion photons for each proton, you have something like 0.3 electron volts here, and that's the energy scale that separates the universe when it's ionized and when it's neutral. Now, knowing this, we can make an incredible prediction. This prediction was first done by George Gamow in the 1940s and 50s. He didn't know really the numbers at the time. He didn't know exactly how much radiation was out there. He was kind of guessing. He didn't know that this was going to happen. He didn't know exactly when this was going to happen, but he knew it had to happen, right? And he predicted the following thing. When you go from an ionized state to a neutral state, something critical happened between these two guys here. Imagine what happens to photons as they propagate in the universe at those early times, okay? So let's see. Before this, let's call this Z. I'll call this, for reasons that will become here clear later, Z deck. So before this T deck, that means Z larger than Z deck, what we have here is that the universe is filled with protons, electrons, which are not bound by the protons. By the way, the universe is neutral, okay? There's no net electron charge. Now imagine that a photon is coming about here. What happens when it reaches, well, it's really inside the plasma, but you can imagine that's traversing some kind of this charged plasma here of protons, of electrons. What happens when light hits charged particles? Sorry? A pinball, excellent. Because of course, a charged particle will be excited by the radiation, will oscillate, you have this dipole radiation, so it will scatter light. So what happens is that will be going for, and by the way, this happens to electrons much more than protons, right? And why is this? Because electrons are lighter, it's much easier to move them around with the photon than it is for the protons. The protons are 2,000 times heavier than the electrons. So the electrons are really doing the hard job here of scattering. So every time this radiation gets to an electron, it is scattered to the other electron, to the other electron, to the other electron, to the other electron, and so on and so forth. So the free mean path of the photons is really small. The universe, we say, is opaque to the radiation. So at that time, it's like you are in a fog, right? The fog means that light is always scattering in something. You cannot really see far away. The mean free path, if you're driving in a foggy day, is maybe 10 meters, 20 meters. In the universe, that free mean path was also very small. So that means the light doesn't really go anywhere. It's just strongly interacting with the baryonic matter at the time. However, what happens after this deck time, so at z smaller than z deck here, is that now, instead of having the protons and the electrons being ionized, what we have now are neutral atoms. So I'm just drawing hydrogen atoms here for simplicity, but of course there's also about 25% of helium here. So now the photons, they come here. There are no charged particles to oscillate, so they just go on like there's nothing. So the universe is basically transparent now. Of course, this process doesn't happen instantly. It is a process of getting the electrons and joining the atoms. You can make a calculation about this and realize that this actually happens pretty fast. So this transition from an opaque to a transparent universe is very quick very quick in a cosmological sense. It only takes a couple thousand years. By the way, this T deck here is approximately 400,000 years. This Z deck here is approximately 1,100. Okay? And in terms of Z, this process takes about Z of 50. So it starts at 1,150, ends at 1,050. So it's kind of quick. So this means that of all the photons that were going around like crazy here in an opaque universe, of course, it's always propagating this way, but I'm just drawing here as a... So when this instant comes, when the universe becomes opaque, becomes transparent, they are not doing this pinball machine anymore. They start to propagate, and they never hit anything else, pretty much. And some of them, of course, they eventually reach our telescopes here, and we observe them. So at some instant in time, very quickly, the electrons decouple from the baryonic matter. Of course, it's only interacting with the baryonic matter. It's not interacting with dark matter. I'll talk about dark matter in a second here. Okay, so this means that at that instant in time, you start to be able to see all this radiation. You can make a calculation based on how many electrons are out there in the universe, how many free electrons are remain after this time here, and realize that actually more than 90% of these primordial photons, they don't interact with anything. They travel to Earth, or to anywhere, by the way, until redshift of 0. So from a redshift of about 1,000 to 0, more than 90% travel and never hit anything. So it's like you're seeing an almost perfect picture when you look here, right? So we are here on Earth. And what we see is a near perfect picture of a spherical shell around us, where you see photons coming from every direction. Here, right? And these photons, they come to you, they never hit anything else, so this is a spherical shell around us of Z approximately 1,100. So that means this is a picture, a literal picture of the universe at that time. It turns out that the radiation that you see today is, of course, you don't see photons. It's not a delta function distribution. You see photons of a wide, of all frequencies pretty much. But the fact that the photons were strongly interacting with matter up to this point means that they were in equilibrium with that fluid of ionized baryons and electrons and so on. So it turns out that this is an equilibrium distribution. And it's, in fact, a Bose-Einstein distribution with a temperature that you measure today of approximately 2.79 degrees Kelvin. And if you look at this temperature at decoupling, this was about 3,000 degrees Kelvin, which, by the way, is the same temperature as the sun, which, by the way, is what you expect, because the sun is kind of similar to this. The photons inside the sun are also doing their own pinball, and then they decouple from the ionized matter in the sun at the surface of the sun, and then they come down to us. So it's a similar temperature, actually. But that temperature was basically redshifted, and now it's 2.79 degrees Kelvin. By the way, this is an almost perfect equilibrium distribution. It's a black body distribution, right? And we measure this to extreme accuracy. We measure this black body distribution here with, there's no deviation that we can measure from black body distribution. Of course, at some level it has to be, because if you look on small scales, on sufficiently small scales, you eventually have to find some sort of deviation from equilibrium, but we haven't found yet. It's the best black body that was ever measured, some people say. So this is basically the intensity of the emission times frequency here. Okay? So now what do we see here when we look at photons that are coming from this patch of the universe, or from that patch of the universe, or from this patch of the universe? Okay? Your telescopes point there and there and there. These telescopes have to be special telescopes. These are not your regular optical telescopes, because, you know, a radiation with a temperature of 2.7, 2.8 degrees Kelvin is actually in the microwave region. So they have wavelengths of, you know, millimeters, centimeters. So these are more like radio telescopes. Yeah, kind of like radio telescopes, but not exactly. They work in a sort of a intermediate between optical and radio telescopes. Radio is really more like many centimeters, meters, and so on. So what do we see when we point our telescope to these regions is that we see something very interesting. We see that the mean temperature here is this 2.79 degrees, but the temperature in each one of these regions is not exactly that 2.79. It's something like this one would be 2.792. This one here would be 2.787. This one here would be 2.7905. This one here would be, this would be, I don't know, 2.7901, something like this. It has fluctuations. So, let me use a... So these fluctuations are telling us something about the state of the universe at that time. So there are fluctuations in this, let's call this the temperature of the universe. Turns out that if you measure the root mean square temperature deviation, so this is root mean square here, of course, the mean. So if you compute for each point that you measure the deviation from the mean of that is, of course, 0, because the mean temperature is the temperature of the mean, of course, right? So this, the root mean square here, is approximately 10 to the minus 4, 10 to the minus 5. It depends on whether you're looking at a small region or a slightly larger region. Okay, but that's the scale of these fluctuations. It turns out that this is also the same scale of the density fluctuations. Because, of course, the temperature for photons, as you know, because of Wien's law for radiation, the density goes like 2 to the 4th, right? So they are related, right? So you know that the temperature and the density fluctuations are also of the same order, 10 to the minus 4 to 10 to the minus 5. Okay? So that's a very interesting observation now. So what we have found, so just to be clear, this, by the way, I didn't give it its name yet. Okay, here. So this is the cosmic microwave background, or CMB. Okay? So the cosmic microwave background is giving you a picture of what the universe looked like. Not the entire universe, of course, but a certain spherical shell around us that we believe is typical of the universe at that time. So that gives us a template for what the small deviations from perfect homogeneity and isotropy needed to be. They were at the time. Because, of course, if the universe was perfectly homogeneous and isotropic, we would never be here. Right? The universe would still be perfectly homogeneous and isotropic. There must have been some initial fluctuations, some initial perturbations that, with time, grew to become stars and galaxies and us. Yes? Everything that happened to that point is manifested in the CMB. Well, not everything, because everything that is connected with the radiation, right? So every process that affected the distribution of matter and radiation in the universe is, to some level, present, manifested in the cosmic microwave background, right? It is the main source of information that we have about the early universe. There's also some information from the formation of the first nuclei, helium, deuterium, tritium, and so on, but that is much more sketchy. Let's say the pristine, precise observation about the early universe is from the CMB, and it carries information about these, what types of matter were present at the time, what were the physical mechanisms, right? Now, it's important to realize that all that you need to compute this is to know approximately the amounts of matter and radiation. You have to know general relativity to know how these components gravitate. And everything else that you need to know is basically atomic and molecular physics, which is, let's say, not an issue, hasn't been an issue for at least 50, maybe 80 years, right? So this is really simple physics. I mean, it's not simple in terms of you have to believe general relativity, but there are so many tests of general relativity now that, you know, it's basically beyond dispute. So the CMB is a very important constraint. It's very simple. In terms of the equations are general relativity and atomic physics. That's it. The system is complex because you have to put it all together in an expanding universe, and you have to use general relativity, but it's really simple, right? And besides this, these fluctuations were very small, right? Which means that any deviation from perfect homogeneity are sufficiently small that you can use perturbation theory. It's going to be an excellent approximation. If you look at the second order terms, they are like 10 to the minus 10. They're surely negligible. Okay, so this gives us some really important information. This is, by the way, these are the seeds of the structure formation. Okay, if you look now, let's say that you looked at the density in a certain region of space here. Let's just choose one direction x here. Let's say that at some instant in time, this density here, let's do the following here to be more precise. Let's say, let's divide the density by the mean density as a function of time, okay? So this would be, of course, the mean is 1. And if you look at each region here, I'll grossly exaggerate this, but you have small fluctuations here, right? These are of order 10 to the minus 4, 10 to the minus 5, right? This is basically what you see in the CMB. Of course, you don't see x, you see an angle, but that's pretty much the same thing. You had a question? Something faster than light? No, definitely not. No, that's a very good question. I'll come to this right after what I say here. That's my next issue here. Your colleague here was asking, well, how come that these temperatures are nearly the same? How did they agree? How did they come to agree that what happened that made these regions know about each other at such an early time, given that, you see, we are here, we're looking at two completely different regions, and this is coming from really far away. This is coming from really far away. There's no way that these two regions were in causal contact before. And I'll come back to this right in 5 minutes, okay? Any more questions about the CMB so far? Yes? A flash of light. Well, it's a flash of light. You think about a point where the light is coming from that point. In this case, the light was already there, but it wasn't freely moving. It was there, and then you release the light at that instant in time, and then that light goes everywhere. Of course, we are here. We are looking at photons that happen to be coming to us at that time, but you have to realize that at the same time, you had light going that way, that way, that way, that way, and that light we never see. Somebody else is going to see them, or nobody's going to see them, right? This was going like this, like that, like that, like that also, right? Every point they had radiation, they had a bath of radiation, and you release that radiation at that moment, and then it travels. So the universe is awash with this radiation, which is traveling everywhere. And if we look at that radiation that's coming to us, then that traces back to one of these regions here. Here or there or there or there or there or there. Okay?
Yeah, my question was whether or not neutrinos have a similar constraint.
Yes, so neutrinos, they decoupled not at this time. Neutrinos actually decoupled around this time here. All right? Neutrinos, yeah, they decouple because they effectively are not interacting anymore. The last time they interacted strongly with matter was around the time of nucleosynthesis here. That's the last time that they basically interact via the beta decay, inverse beta decay. These were the main processes at the time. So the neutrinos were in equilibrium basically up to this point. After that, they dropped out of the equilibrium because neutrinos are really dark, right? They don't really interact with anything. So we do have a bath of neutrinos also, which are permeating the universe, but we haven't been able to detect those neutrinos yet. There are plans to do this, but these are really, really, really hard. Neutrinos are super hard to see even when they are highly energetic. So to see these neutrinos have a temperature which is even lower. It's about 2 degrees Kelvin, right? Anybody knows why the neutrinos have a lower energy than the photons? Neutrinos, they decouple earlier. Actually, they decouple before something happens, which is, okay, so let me go a bit further. Around this time here, the universe has about 0.2 to 1 MeV. Now, what is the rest energy of an electron? Sorry? 0.5 MeV. So what happens when you have a temperature which is above the rest mass of a particle like an electron? Well, there's enough energy in any photon that when it hits something, it can create a pair of electrons and positrons. So you have enough energy out there to have pairs of electrons and positrons. By the way, those are the most abundant pairs because those are the lightest particles. So what we have above this energy scale here is that we have not only the electrons, but we have a huge amount of electrons and positrons lying around, bouncing around. There's a share of the energy of the universe which is in these pairs of electron and anti-electron. There's also a slight over-density of the negatively charged electrons because the universe is neutral, right? But there's a huge amount of electrons and positrons. And when the energy lowers enough, most of those electrons and positrons will annihilate, and they will turn into photons. Now, it turns out that this process of electron-positron annihilation happens a little bit after the neutrinos decouple. So the neutrinos don't inherit that energy. So they have a lower temperature. Okay? So you can actually calculate this, but I wasn't planning to talk about this, but somebody asked, so. Okay? More questions about this? Yes? That's an excellent question. That's my last lecture, which is called structure formation. By the way, I was going to start talking about this in here. So let's say that this is the initial density of some region that we are observing in some direction here. So these are the fluctuations, right? The mean is 0, but they have an RMS of 10 to the minus 4, 10 to the minus 5. So I grossly exaggerated the amplitude of these fluctuations here. Clear? Now, without having to know even general relativity, what happens if a region here has some overdensity here? So that's rho here. If we can write this in terms of the gravitational potential here, what happens is in that region you have a gravitational potential which is like that, right? So what happens with the matter which is over here? There's a gravitational well there. It wants to fall there. When it falls there, what happens? It becomes denser. The gravitational potential becomes deeper. You attract more matter, and so on and so forth. So gravity is doing this, of course. So gravity is a driver of inequality, if you want. Whoever has more gets more and more. And the person that starts with little here, like, so this guy, so it was like this, and then with time, it goes like that, and so on. So the emptier regions become emptier. The denser regions become denser. So this process here, so let me draw this. So it turns out that we will calculate this in the next lecture, but this process here is, in the beginning, is very simple. The beginning of the structure formation here, it happens in this fashion that I'm trying to draw here. Maybe you're not seeing because I'm drawing really small, but I'll start exaggerating here. Okay, let me draw again here, now much later in time. So you get the idea, right? So what's happening is that the dense regions are becoming denser, the underdense regions are becoming underdense. Turns out that this process here, you can describe very well in terms of this, let's say, delta rho over rho bar, is proportional, actually, in the linear regime. So when perturbation theory is good, when the perturbations are small, this goes like the scale factor, in fact. That happens in a matter-dominated universe, and we will calculate this in the next lecture. So I will show you this. I'll not just tell you that this is how it is. Okay? There's an equation that you can solve for this. Okay? Yes? How massive, what? Excellent question. So your colleague's question here was, knowing what these fluctuations were initially, can you then predict to some level the masses of objects that you have today? Of course you can. That's the whole issue of doing structure formation. You can predict not only how massive they have to be, but also how these positions of these peaks and troughs of these fluctuations, where they have to be with respect to one another. You see, we don't know only the amplitude of these fluctuations, but also the distribution of these fluctuations. Because, of course, these are kind of random, but they have a pattern, okay? So there's a pattern. There's a correlation between the positions of peaks here. So it's true that any given region has a random possibility of being either more positive or negative, whatever, but it's not random that you find these peaks separated by some distances. That's not random, okay? I'll talk more about this in the next lecture, but that's a very good question. So by starting with those initial conditions, by using the equations of physics, general relativity, atomic and molecular physics in the beginning, later just general relativity is fine, propagating them in time, you can make those predictions. And then you can test with observations, because then you will see now the result of that process. Yes? This is how we know, sorry, what? This is how we predict how the universe should look like if our theory is correct. And then we can compare with the observations. That gives us the initial conditions. The CMB gives us the initial conditions. The physical laws are those physical laws that we know today. General relativity, atomic and molecular physics are enough. They seem to match, with some, little problems that I'll discuss also. Okay, so now let me go back to a question that you asked. That was, how it comes about that these temperatures are nearly the same. So to see the magnitude of this problem here, let's make another plot here, which is basically a plot that I did in the last lecture. And I'll revisit that plot here. So we saw that if the universe is dominated by matter or dust and radiation, we computed the light cone here, right? So we are here in today. And we computed the light cone here. And we saw that it has this funny behavior here. It actually has a horizon in the past here, right? This is what we saw in last class. That's just Friedmann, Lemaitre, Robertson, Walker with matter and radiation using Friedmann's equation. You substitute to make the integral. That's basically what this is, right? Remember that we used alpha at the time. We use A goes like to the alpha, but alpha is equal to 2/3 for dust, and it's equal to 1/2 for radiation. So that's the picture that you have, okay? Of course, there's a transition somewhere over here, but it doesn't change the qualitative character of this, right? It's basically a picture like this. Now, imagine that, let me draw here the instant in time when you form the CMB. So that's the instant when the radiation decoupled from matter. So those photons that I drew there, if I'm looking at two pairs which are coming from opposite directions, they would be coming from here, right? So this is one of them. Okay? And we saw that this one here, for instance, had the 2.792 Kelvin. And this other one here, that those photons that came from there had the, I don't know, 2.7901 Kelvin, something like this. Very similar, but slightly different. Now, whatever processes and whatever happens in the universe up to that point here that created a nearly thermal equilibrium at this point here, they all had to be coming from whatever the past of that guy is. And if you draw the past of that guy, it's over here, right? That's the past light cone of this event here. And the past light cone of this event here is this one. So now you see the problem. So this is the past of point A, and this is the past of point B. So in this, let's say, traditional standard model of the hot Big Bang, not only we had a horizon in our past, but these points had an even smaller horizon when the radiation was released. How come that, given that these pasts have nothing to do with each other, how come that these temperatures are nearly the same? It's like the universe had to be created over here to start with the same temperature and the same density almost everywhere. Somebody needed to know, somebody needed to violate causality to generate those initial conditions over here, right? There's no causal way to do this. So there's no causal mechanism for generating these initial fluctuations. There's no physical mechanism to do this. You would have to violate something which is even more basic than general relativity here. You would have to violate even local Lorentz invariance to do this, which is a no-no. Right? So, there seems to be no way out of this problem here, at least in the standard model. So, there's a way around this, which is to realize that as you go back in the past, we know very, very little about what the universe looked like. We know what the universe looked like from here on. That we know relatively well. We know a little bit more about the region close to the CMB. We know something about the universe in the time of the nucleosynthesis, but if you go beyond that, we know almost nothing. So we don't really know that the universe was dominated by radiation and matter. So in the 1980s, so about 40 years ago, some people proposed the following scenario. Well, let's say that I can create a small phase here in the very beginning of the universe, and I'll blow up that small phase by a lot here. Let's say that universe started a little bit earlier here. Okay, I'm just exaggerating here grossly, okay? Again. Where in this epoch here, the universe was not dominated by matter radiation, but it was dominated by something that made the scale factor go like T to the alpha, with alpha much bigger than 1. So that means an accelerating universe. Now remember what happens in the past light cone when you have acceleration. Well, acceleration means that earlier it expands slower and later expands faster. So if it expands slower, this means that you can actually, your past light cone becomes wider and wider and wider like this. Now what happens is that the past of these guys here, they do overlap. And in fact, if you do your job well enough, you can make the past of everything which is in here to overlap. And now it makes sense. Now you can say that all of these regions here, they emerge from the same past. So that's a mechanism. So that's not enough, by the way. That's just you allowing for there to be a mechanism to generate these fluctuations. It turns out that this phase here, which is called this accelerated phase of expansion in the very early universe, is called inflation. So it turns out that inflation not only has the possibility of generating these fluctuations in a causal way, but it also does generate them in a fascinating mechanism, okay, which basically you start with a perfectly homogeneous universe and you end up with small fluctuations of the order of this 10 to the minus 4, 10 to the minus 5. Okay? I won't have time to discuss that, but it's in my slides, in my lecture 4 of my slides. Okay? So there's a way out of this, but you have to change the model. You have to introduce some new component. And then, of course, once you introduce something new, you can then go and check if the predictions of that new model square off with observations. So far, seem to be that they are squaring. So this inflation makes some predictions about the nature of these fluctuations in the cosmic microwave background, and they are consistent. But they are not yet a proof of inflation. For this, we will need to observe something called the primordial gravitational waves, or some deviations from this pattern of these Gaussian random fluctuations, which we haven't seen so far. So it's unclear. Anyway, let's say that everything is consistent with this idea here. Okay. Well, I'm moving embarrassingly slow, but I still wanted to talk to you a little bit about dark matter today. Anyway, yes. Yeah, you can make this calculation here in terms of the radial coordinate, and then you can just extend this to.
How would these lines look like? How are plotted at the proper length away from me?
You mean physical distance? Yeah. Well, the physical distance, it gets tricky because you multiply by the scale factor, so you won't see. So what happens is that as you go back in time, the scale factor goes to 0, so these regions, they are kind of collapsing like this. But looking in physical distance is always a bad idea if you're talking about the causal structure, because you're not really seeing it. So you're basically, all of these, they are collapsing to a point here, but everything goes to 0, but they go to 0 in a different way. So the only way to see them is in co-moving coordinates. It's like you're doing a diagram. You don't want to look at the causal structure in physical coordinates, just like you don't want to look, I mean, in some cases it's better to look at the Penrose diagram because of the same reasons.
But just so it grows and then eventually collapses. When does it start collapsing?
When this starts, well, then you have to extend this model more and more to some initial time. So whether or not there is some kind of a big bang over here or something else.
So it starts growing.
Yeah.
And then eventually there's a point where it reaches the maximum and then it starts going down, the proper length, right? Of the light cone. I'm asking if it, around what time scale is that?
This time scale here. What, I mean, what do you mean by proper length here? I'm not, it's not clear.
If I follow the light cone to the path,
Yes.
the proper volume of this light cone,
Yeah,
it
it's,
grows, but then it decreases, right?
well, no, no, it's always growing. The question is whether the rate of growth is decelerating or accelerating. What you proper is moving or not? I don't know what you mean by proper. It's physical. The physical volume. No, the physical volume is, yeah. So the physical volume grows and then it has to go down. Exactly when, I don't know. It depends very much on the model now, but I don't. But it doesn't really have any meaning. This.
Just for curiosity, is it around this recombination?
I don't. No, I think it has to be over here somewhere. I mean, let's see. I don't know actually. It's probably around here somewhere, but I don't know. It's a balance between the light cone and the scale factor that for each one of these scale power laws are maybe different. I don't know. I haven't. But it really doesn't, I mean, yeah, it doesn't really carry physical information that's relevant here. That's the important thing. Yeah. Yes. So basically, so let's, yeah, I'll give up on talking about dark matter today, okay? Tomorrow. So let's say that I do my diagram again here of the densities, right? So again, let's say that this is the cosmological constant here, or dark energy. Then we have, let's say, matter. Then we have, let's say, radiation here. This new component here, I don't have any colors left, so I'll just do it in white. This new component here needed to be much larger. But then it needed to decay eventually to give rise to the universe that we know, which is this one, right? Which is the one that we actually observe, right? Is this. So how you do this, it's certainly not with a cosmological constant, because then you would have something like this. And you'd be forever dominated by an expanding universe that's completely empty, that's good for nothing, right? So the way that you do this is through something called a scalar field. So basically, you create a new field that has an expectation value on the universe. So it's like, it's a kind of a number. And you give it a potential, and it's slowly going down that potential. That potential gives that, let's say, effective cosmological constant, but it decays with time. When it reaches the bottom of the potential, then it basically evaporates, or it disintegrates into the particles that we see today. So, sorry? It's unclear. We know that it has to go away, because if it's there forever, then the universe doesn't look like anything like what we have, right? So there are concrete models for this. It depends on, there are mechanisms that you can do it in a smooth way. There are mechanisms where there's basically a phase transition. You come at the end, and then everything basically disintegrates into the particles of the standard model. But it's unclear exactly which mechanism makes that transition. And that transition, by the way, doesn't leave any trace in observations, which is kind of the trick here. It's not clear, and it's probably going to be undecided, because it doesn't, that transition itself doesn't really, it's not reflected in any observations that we can have, not even in the CMB, as far as we know. Maybe some exotic scenario could leave signals in gravitational waves or primordial black holes, but maybe in some exotic models. Okay, all right. I think I have to stop now because my time is up. Or is it up? Yeah, it is up, right? 9:30, 10:30, yeah. So I'll continue next class with some of the main embarrassments of cosmology, dark matter, dark energy, the Hubble tension. I'll also say a few words about structure formation in next class, which I was hoping to dedicate the entire next class to this, but you know, we'll have to do only about 15 minutes or so, but it's usually enough. Okay, more questions? Thank you. Yeah, go ahead. What?
How much information can we get from the CMB, and when will we need to go to, I don't know, see neutrinos or gravitational waves?
Okay, so that allows me to go into a bit more detail about the CMB, so thanks for the question. So let's see. Yes. No, I won't eat into the coffee break, literally. So where should I draw this? I'll draw it there. So let's see how we actually describe the information on the CMB. So let's say that we are here, right? And we're observing that spherical shell around us, and all the photons that are traveling from everywhere to us. And then what we can do is that we can do a map of those photons, right? And then you can, a way to see this is not by drawing a sphere like this, but is doing like a world map inverted. So this is the equator, basically. You choose some coordinates there, it doesn't matter. And then this is north, this is south, and this is the equator, and you're looking out instead of looking in. It's an inverted map, right? And then when you do that, you find that there are all these fluctuations here. Of course, the mean temperature is that 2.79 Kelvin that I told you about, but this is a kind of a random map here. Draw this in this color, and then in that color also here, so that you see that there's always something in there. Sorry, I'm being a bit excessive here, but just so that you have an idea. I could show you a picture, but it would take more time to get the picture in my laptop or my... And then also some regions here which are hotter, cooler, whatever, right? It's kind of a random thing here. So now, so this is the pattern that we see. Kind of fluctuations on all scales, by the way. You have small regions, you have larger regions. It's kind of a mess. So we know some things about this fluctuation field here, which I'll call just delta of theta and phi, right? So this is what we see. This is delta T over T bar, delta T of theta and phi. So the temperature fluctuations. We already know they are order 10 to the minus 4 and minus 5, but how do we actually quantify them, right? Well, first of all, we have to do some kind of statistics of these fluctuations. So basically, we have to look at, well, first of all, their expectation value is, of course, 0. But then you can look at the statistics at the second momentum of the distribution, such things like delta t square, right? This is the RMS there, but What I haven't specified here is about if I'm doing this delta t square here in a region like this, in a region like this, or in a region like this. It depends on the scale that you're doing this, right? So in order to do this, this representation in terms of a map in degrees is deficient. What is the best possible way that we can represent this delta t, which is a scalar field on the sphere? So what is the optimal basis to represent these functions here? Well, spherical coordinates I'm already using. But what is the basis functions that represent scalar functions on the sphere? Spherical harmonics. So you represent this in terms of these spherical harmonics right? Like this. So you have these coefficients now, right? Now, remember that L is giving you how these Legendre functions oscillate between cosine of theta of 1 and minus 1, and the larger the L, the more they oscillate. So the L corresponds to some scales which are, if they are large, then L is small, and if they are small, L is large. This L here, right? So now you can ask the question, well, instead of doing this, we can do this, right? That's a more apt question. And you can ask what this looks like. It turns out that this has the following interesting properties. So first of all, it's orthogonal in the, let's say, L and M space. And then the amplitude is just given by something which we call CL here. So this is basically the variance of this field here. So it's this guy here, which is what I'm calling the RMS. It turns out that you can do higher order statistics with this, and then you find that delta t is what we call a Gaussian random field. Okay? So Gaussian random field means that the only momentum of this distribution is the second momentum. Everything else is, you can rewrite in terms of the variance if you want, right? And they are unrelated. So if you look at L is equal to 10, it's unrelated to L is equal to 11 or 5, and vice versa. So they are uncoupled. So it's, the different scales are different degrees of freedom if you want. So that simplifies the issue, because now we know that this is a Gaussian random field. We only have to look at these. So all the physics has to be here on these CLs, right? What happens when you plot those CLs? You must have seen, surely, some of these plots, but I'm putting them here anyway. So this is L, and this is CL here. So what we find is that they have a certain shape here, which looks like this. The amplitude of these CLs is typically 10 to the minus 4 squared. That's the 10 to the minus 4 that I told you about here, okay? So we can measure this, and we do measure that. So we have all these points here for each L that we can measure with our telescopes. The best experiment that measured this was the Planck telescope, which is not working anymore, but you have also more recently things like the Atacama Cosmology telescope and others also, okay? This is our theory for what the CMB has to look like. This is the data here. So that theory has only 7 parameters. and you have thousands of points here, and they agree almost perfectly. So what's happening right now, to answer your question finally, after all this digression, is that these points here are already observed. There's nothing more that you can do. The statistics is saturated. You can put another satellite out there. They're going to measure the same thing. By the way, does anybody has any idea how long we have to wait until the cosmic microwave background changes? Because, of course, if we wait some time, we are looking not at this sphere, but at this sphere. How long do we have to wait for the cosmic microwave background to change by, I don't know, 0.1%? Millions of years. So forget it. You're not going to see a change in your lifetime. So if you put a telescope out there again, you're going to see the same thing. However, as you go to smaller scales here, it becomes harder to observe because you need to have a really good telescope that can resolve those small angular scales so that you can measure L of 2,000, 3,000, and so on. And for this, there are new telescopes, mainly on Earth, which are not observing the whole sky, but small parts of the sky with very high definition. And there you can start to see some more interesting effects, because then you're starting to look at small scales. On small scales, the universe is a bit more inhomogeneous. There's weird stuff going on in there, like some processes which are, the universe is not in perfect equilibrium anymore, and there's gravitational lensing going on, so there's something going on in this area here. So on very small scales, related to gravitational lensing and small deviations from equilibrium. Okay, so we call these spectral distortions.
Okay, one question, if the answer is short.
Short is like yes or no? Or I don't know.
I can make it a yes or no question.
No.
Well, I feel like I already know the answer, actually. Well, it's about the expansion, the inflation. Do we have any hypotheses to explain why it happened or why it would have to happen?
Why?
Yeah, like, it happened. There must be a reason why it happened. It seems so unnatural to just have a...
The question is whether or not it does anything that you can see in nature, right? Physics is about asking what's out there.
Yes.
And so I could be, I don't know, a kind of a string theorist and said, why, my God, why is it that the universe is doesn't seem to be described by string theory? It's so beautiful and so nice, I love it so much, but the universe is not like this. Why, oh my God, why? Okay, you can live with that if you want, but the question here is not about why the question is, why is the CMB so homogeneous? That is the question. It doesn't have an answer that makes sense unless you change the past here in some way. It can be in this way through inflation. There are other mechanisms also which are a bit more contrived in such a way that in the very, very early universe, there was a contracting but slow phase of contraction that then becomes an expansion, but those models are they don't really work too well.
So the inflation
So
is
the question of why is a bit, beyond physics. I mean, why is general relativity the theory of gravity? It's the simplest one, it's the most beautiful one, I don't know. You can live with those.
Okay, thanks.
Okay, all right, guys. See you tomorrow.